Yeah, I started. Yeah.
Okay, so hi everybody, welcome to Quant Talks. Today we have Paul Barclay presenting. Paul is an associate professor at University of Calgary, Canada. He completed his PhD in applied physics at Caltech in 2007, where as one of the first students in the Painter lab, he created silicon nanophotonic devices for experiments in nonlinear optics. He has also collaborated with atomic physicists to study light matter interaction using chip-based photonic devices and atom traps. In 2008, he joined Hewlett-Packard Labs, HP Labs in Palo Alto, California, in USA, where he advanced the emerging field of diamond quantum nanophotonics. Since starting his lab at the Institute for Quantum Science and Technology at the University of Calgary, Canada, he has performed pioneering research in the field of diamond photonics and optomechanics. Today, Paul will discuss novel nanomechanical devices for creating a new interface between light and quantum memory based on diamond NV center electronic spins. So feel free to interrupt Paul for questions. As for bookkeeping, please mute yourselves at all times. If you have a question, please raise your hands, use the raise hand button, and I will interrupt Paul at an appropriate time to ask the question. Paul, over to you.
Okay, thank you, Akshay, for the kind introduction, and thank you for the invitation to speak, I guess, virtually at your institute, and I hope to visit in person one day. So just to begin, I'll say that my talk today is focused on work that my group has been doing in diamond nanophotonics and optomechanics. We also work in building silicon optomechanical devices as well as nanophotonic devices from a range of other materials. So really, as a sort of general lab focus, we're motivated by creating nanophotonic devices from whatever our favorite material is for doing quantum experiments ultimately. Okay. So the title of my talk today is Dive in Caveat to Mechanics, Interfacing Photons, Phonons, and Spins. And this encapsulates work that we've been doing in my lab at the Institute for Quantum Science and Technology for the past 10 years, starting from developing simple devices from diamonds to our most recent work in which we couple light into a diamond optical cavity. This is represented here by this microdisk structure, which supports an optical resonance. And we have recently shown that we can use this light to excite mechanical motion in this device, and through that motion, control the state of impurities, which are impurities in the diamond, which are spin qubits, thereby creating a new form of photon to spin interface that relies upon optomechanics. Okay, and I'll motivate why we want to do this and talk about all the work that went into this over the next few slides. And I should mention that, or encourage you to interrupt if you have any questions. We should have lots of time to go through all of the material. And I'll also mention before we get going that all of the devices that you see in this talk are fabricated by group members, students and postdocs, working typically at the NanoFab, which is a fabrication facility in Edmonton, located about 300 kilometers from Calgary, which, and as well as the National Research Council Nanotechnology Research Center, formerly known as NINT, which is also located in Edmonton. So in our group, we do device design, fabrication, and experiment. Okay, so the broad motivation for this work comes from the field of quantum networking, which some of you may be familiar with already. And the idea is that with the emergence of quantum technologies, we'd like to be able to find a way of connecting different quantum systems over either short distances on chip or long distances, through telecom fibers, and in this way build a sort of quantum internet which consists of quantum nodes connected through some sort of quantum channel that entangles them and allows us to exchange information between them. So one version of this might be, to have some network of quantum processors that aren't so different from the computers that classical computers that we work with today, that are networked through some sort of means. And in many of these applications, these networking links, these quantum channels, are typically photonic in nature. And a big challenge is figuring out how to, coherently couple light to these individual quantum nodes. So this is typically imagined as being done using a form of optical resonator, represented here by two mirrors, inside of which you have your favorite qubit. And the purpose of the resonator is to enhance light-matter interactions between the qubit and ideally a single photon. And basically the idea is that when you, if you have a single qubit and you fire a photon at it, unless that photon is really tightly confined and interacting strongly intrinsically with that qubit, it probably won't, coherently transfer a significant amount of information to it. If you then embed that qubit and photon inside a cavity, that will both increase the interaction time, the rate of the number of attempts you have, if you will, for a photon to couple to your favorite qubit, as well as if you bring the mirrors together, really close together, it'll increase the rate at which that photon interacts with that qubit as it bounces back and forth between the mirrors. The closer those mirrors are together, the more often it will, per unit time, it will interact with that qubit. So basically, through photonic design in the form of cavities, we want to enhance light matter interactions in order to realize such a network. Okay, and in some systems, this is really what these nodes and links look like. We have actual, groups in the atomic physics world, like Kimball's group and Rempe's group, and many others, really build these types of systems. In my lab and in many other labs around the world, we endeavor to find solid state versions of this system, where instead of maybe trapping a single atom inside a cavity, we find some sort of solid state qubit. This could be a quantum dot, for example, or in the case of the work that my group has been pursuing, it could be an impurity in a crystal. Much of this work over the last 10 years is focused on impurities such as the nitrogen vacancy center in diamond. So this is basically, if you take a perfect diamond crystal and you replace one of the carbon atoms with a nitrogen, and you place that next to a missing carbon atom, so a nitrogen and a vacancy, you can find that this impurity behaves in many ways like a trapped alkali atom, in the sense that it has well-defined ground states, well-defined excited states. These states are coupled through optical transitions. In other words, they can emit photons, and they can do this strongly enough that you can actually optically measure single impurities. So this is a confocal microscope image of a diamond sample. The field of view is probably about 100 microns by 100 microns. And each of these bright spots is light coming from a single impurity in this diamond sample. And the color in this case corresponds to polarization and not wavelength. In principle, the photons coming from these emitters are all identical. Although this in practice is a little bit difficult to achieve. Furthermore, this impurity has electronic spin states, so like fine structure in the ground state, that has excellent coherence properties and can be used as a quantum memory. And very fortuitously, the coherence properties of these spin states are really fantastic. So at room temperature, you can, if you were to place the electronic spin of an NV center into a specific ground state, it can stay there for around the order of milliseconds, maintaining like phase coherence. And that's at room temperature. And then even more remarkably, it's possible at room temperature to easily read out the state in which you're in using just an off-resonant green laser. Okay, so without really getting into more details, I just want to say that impurities in diamond, as well as other semiconductor crystals to varying degrees, can emit single photons, and they can function as quantum memories in much the same way as like a trapped ion or atom of some kind. Okay, so this system has been used specifically this diamond system has been used in a large number of sort of groundbreaking quantum experiments, which are pushing towards building these quantum networks. There's a nice review from the Hansen and England groups on the archive this year. One of the more famous recent experiments was this loophole-free violation of Bell's inequalities by the Hansen group in Delft, in which a diamond at point A on the Delft campus is entangled with another diamond at point B on the Delft campus through an optical link, and in a way that violates Bell's inequalities in a loophole-free manner due to the large distance between these qubits. And more recently, this is also from the Hansen group, they demonstrated the first realization of a sort of multi version of this network. We now have 3 different diamonds that are entangled optically through quantum sort of optics techniques. Okay, so I could also talk about how these qubits can be used for sensing and a range of other applications, but I'll stop there for now. Instead, shift towards discussing, what is the role of nanophotonics in realizing in realizing these quantum technologies. And nanophotonics is really important as a platform for potentially wiring these qubits together. So despite many years of effort, there still haven't really been many. Yes?
Paul, we have a question from Sandeep.
Oh, I see. Yes. Go ahead.
So what do you mean by optically connected? Can you elaborate on this a little bit? Like the diamonds you have shown in the previous slide, there are 3 diamonds in different regions and they are connected optically. So yeah. What information is being passed between these? Can you elaborate on that part?
Well, they're being maybe go back to the more simple experiment. They emit single photons, okay, and A and B, which are indistinguishable. And at C, those photons are interfered. Okay. And this creates entanglement between the qubits at A and B. And I should say that, of course, there's various different protocols, but basically one version would be that, if A or B emits a photon, that A or B is in one of 2 possible spin states. All right. Okay. And if you then detect a photon at C, now you know that one of your qubits is in a specific spin state, but you don't know which one. All right. And that then creates a sort of entanglement between these 2 qubits. Okay, or like creation of a Bell state between qubits at A and the qubit at A and the qubit at B. So that's what I mean for the purpose of this experiment, anyways.
Okay. Thank you.
And then this is an even more kind of complex version of that, but the same principle. By using indistinguishable photons, we can create entanglement between these qubits.
Okay.
And then nanophotonic devices serve the purpose of potentially allowing us to wire these qubits together. So instead of just having one qubit connected to another qubit far away, you could imagine many of them entangled on a single chip. Or even more simply, you can imagine using something like a photonic crystal waveguide with the qubit embedded within it as a device that allows you to really efficiently collect photons that are emitted by these qubits, And this is really important because if you look at these experiments, you see that, they're really impressive, but the rate at which they can entangle qubits, at least in the very first experiments, is quite low, like on the order of hertz, if I remember, or even less. I think something like a few. Sorry, I should say, yeah. If I have to backtrack. Like a few entanglement events per hour, and then that's been improved over the last few years significantly. And what really limits you is how efficiently you can collect the photons that are emitted by these qubits. And I think that the scaling of the entanglement rate is something like 10 to the power of 4 with your collection efficiency. All right, and nanophotonic devices provide the opportunity to do this much more efficiently, and then they also provide the opportunity to create like a more complex nanophotonic network, which I won't get into now. That could maybe allow you to realize a sort of on-chip quantum processor. And so a number of groups have been working for many years, including myself. When I was a postdoc at HP, we used diamond microring devices. So this is like a diamond ring with a few qubits, diamond qubits embedded within it. And we use these structures to just enhance the light matter interaction, which creates a brighter qubit through the Purcell effect. And a number of groups have built on this work over the last few years to continue to use nanophotonic devices to improve the optical properties of these emitters. What my group has been focused on for the past 5 years or so is using diamond photonic devices as platforms for converting information between different mediums. And I'll talk more about what I mean throughout the rest of my talk, basically. So what you can imagine is if you have an NV center, it will be desirable to convert its quantum state to both a photon, but not just any photon, maybe your favorite telecom wavelength photon. So everything I've talked about previously involving NV centers has involved emission of photons at sort of visible wavelengths determined by the electronic structure of the NV center and its optical transitions. But imagine if you had some device, which I'm kind of giving away the punchline here. It's in this case going to be a mechanical resonator, but just in general, some device that could convert that information into a telecom photon. Well, that would be a very desirable property because then you could imagine entangling them over much longer distances. You could imagine wanting to convert that information into a microwave photon for the purpose of coupling to a superconducting circuit, or even finding some more direct path to couple to a superconducting qubit. And the idea is that none of these processes are possible directly, at least with very high efficiency. So an NV center doesn't have any optical transitions at telecom wavelengths. It doesn't couple to telecom wavelength photons. But what my group has been trying to do is using mechanical devices that support vibrations that can be driven optically to realize these types of interfaces. And so throughout this talk, I'll talk about a few different versions of this. So the first one is going to be focused on just the interface between telecom photons and vibrations in diamond. All right, and then we'll build upon that to talk about how we can then couple these to spins. Okay, which is sort of the second half of my talk. So are there any questions now before we dive into the results? Okay, so yeah. No, okay.
I just unmuted myself to tell you can proceed. There are no more questions.
Okay. Okay. So right. So the next few slides we focused on converting light to mechanical vibrations in a coherent manner using diamond nanophotonics. And this is an application of a sort of subfield of photonics called cavi-optomechanics. And the basic cavi-optomechanical system consists of an optical cavity created by two mirrors. And what we're adding to this cavity is the ability for one of these mirrors to vibrate. Okay, which of course exists intrinsically, but we're going to assume that one of the mirrors has a really well-defined mechanical resonance that couples in some useful way to light in this cavity. Okay, so you can imagine light coming into the cavity. It's going to bounce off of this mirror. In the process, it might impart some momentum, or it will impart some momentum onto the mirror, which causes it to move. And similarly, if this mirror is moving, it will modify the reflection of this cavity as a function of time as that mirror moves. Okay, and so just to understand the physics of this, you just need to understand how like LIGO works, for example, where you have a huge interferometer and it's being mechanically deformed, and that's changing the optical response of that interferometer. And this is really no different. Things can become quite interesting if the rate, like the mechanical frequency, is large compared to the time it takes for light to build up in the cavity, so like the cavity lifetime. In this case, the physics becomes quite rich, and you have sort of a feedback effect that you can use, and that we'll talk about through this talk. Okay, so in my lab, though, and in many other labs in the world that have been studying this field of cavitation mechanics over the last decade, the cavities don't necessarily look just like two mirrors, but rather have a wide range of different geometries. So these are illustrated here in this nice image from the Marquardt group. Basically, you could create a cavity which isn't so different from two mirrors, but is created by like a membrane and a mirror. Or you could create a microtoroid cavity where you have basically what's called a whispering gallery mode resonator, where light circulates around the outside of this disk, and vibrations of the disk modify the optical resonance or the optical path length experienced by those photons. In the superconducting microwave cavity QED world, you can imagine creating a capacitor, which forms part of an LC circuit that has a gap, and that gap fluctuates, and that creates an optomechanical coupling. And then in the sort of nanophotonics world, you can imagine creating a photonic crystal cavity, which traps light in some small volume related to the patterning of little holes in a waveguide, in such a way that it couples to vibrations, local deformations of these holes in this structure. And what all of these devices have in common, despite looking very different, and if I show their length scales, you can see that they can be very different in size as well, is that you have light represented in blue here, which is confined to a volume which overlaps and interacts quite well with mechanical vibrations or mechanical resonances, which are represented by these gray kind of squiggles. All right, and basically the goal is to make a system which maximizes the strength of this interaction while minimizing the loss rates of your system. All right, and that is sort of summarized by this slide here, where we have some optical degree of freedom that's characterized by photon loss at some rate kappa. This would be determined by your cavity quality factor. And we have a mechanical degree of freedom, which is characterized by some mechanical quality factor or loss rate. And the goal of our experiments, at least the first necessary step of many of our experiments, is to build a system where the interaction rate, G, exceeds both of these loss rates. And to do this, you basically need to build a small cavity, which gives you large G, and a system with low optical and mechanical loss, so small optical and mechanical decay rates. And as a bonus, you want to be able to put lots of photons into our cavity in order to sort of parametrically enhance this coupling rate, which I'll talk about if there's time. But basically, this means that we need to have a cavity that doesn't suffer from lots of two-photon or other nonlinear absorption. Okay, and so with this in mind, you can convince yourself that diamond is a potentially really good material for building cavitation-mechanical devices. It has a really low optical mechanical loss and has a really low nonlinear absorption, or in other words, it has a huge electronic band gap. Okay, so that's the good part. What's the catch? Well, unlike conventional sort of photonic materials like silicon and 3-5 materials, where you can buy large wafers of thin films, with diamond, although there have been revolutions in the ability to create synthetic material, it still is typically sort of bulk crystals that are grown synthetically, but aren't in sort of a thin film form that you typically require for photonic structures. And so the challenge is, how do we create diamond devices from materials like this? So over the last decade or so, there's been a lot of progress in creating diamond photonic devices. Some early work focused on making photonic devices from thin films of polycrystalline diamond, but these tend to not support NV centers or other spin qubits with good properties for reasons that maybe we're still trying to understand. And as a result, since then, there's been a lot of focus on creating devices from single crystal diamond, so ranging from sort of hybrid approaches where we combine different photonic materials, like diamond with another material, to create a sort of hybrid device. Work from a number of groups taking bulk diamond and gluing it onto a substrate and then polishing it or etching it down so you have a thin film of diamond on top of your favorite substrate that you can then pattern to create photonic devices or waveguides. Ion milling techniques, and also angle etching techniques, which allow you to sort of create like 3D structures from bulk diamond. And my group in Calgary developed a sort of version of this reactive ion etching technique, which basically allows us to undercut diamond using plasma etching. And for those of you familiar with fabrication, basically the steps that we're using are pretty standard in the sense that we take diamond, we pattern it with a mask, we pattern that mask with electron beam lithography, we etch it. Where our major contribution is here, where we found a way to basically use a plasma, which is etching diamond in not just one vertical direction, but also in a horizontal direction at the same time. And we showed how we can use this to create suspended structures like waveguides and cavities. And this technique, actually kind of came after this angle etching technique from Lonkar. I wasn't really sure how successful it would be. I mean, I was happy to do it because it was new and different and had some advantages. We were having difficulty getting this technique to work for us in our clean room. And over the last 5 years or so, it's actually sort of, become the standard technique that most groups, I think, are beginning to do diamond photonics or have adopted as their main approach for making diamond photonic devices, which has been quite gratifying. So these are some of the structures that we created using this technique. This is a diamond microdisk. And basically what you're looking at is a scanning electron microscope image of an array of diamond whispering gallium mode resonators that I'll talk about shortly. And I guess the key point to take away from this is that everything that you see in this image is diamond. So this is like one diamond chip that we've carved a 3D structure into using our fabrication process. And these sharp angles that you're seeing are actually crystal planes of the diamond that are being etched in this very chemical manner by our fabrication approach. And I should mention that the tools that we use for fabricating these are nice, clean room tools, but they're nothing special. Okay, like basically they're standard Oxford plasma etching tools that you would find in most clean rooms in the world. They're not new. They've been around for decades. Of course, it's nice to have a high quality tool which can be more reproducible and these kinds of things, but there's no new exotic fabrication tool that we've needed to use to do this. And the etching chemistry just relies on oxygen plasma, so we're not using any special gases really for doing this.
Paul,
yeah.
I have a small question. So, so you mentioned the improved technique for fabrication. Do you also use the same technique here for preparing these?
Yes, exactly.
And so my question is, how does the new technique help over the older techniques in preparing this geometry?
Yeah, I mean, it's fairly subtle. Like fundamentally, there's no reason why this should be way better than any of these other techniques. it kind of comes down to practical considerations. So this thinning, for example, in principle, would allow you to make great diamond on silicon wafers that you could then pattern quite easily. But in practice, it's quite challenging to realize because you have to etch your diamond from 20 microns or 50 microns, whatever the thinnest diamond slab you can get from the company Element 6 or whoever, down to 500 nanometers. And then you have to stop. And this, from a fabrication point of view, is actually quite hard, especially when you consider that these diamond membranes aren't flat to begin with. They might have, a 500 nanometer variation in thickness across their surface area, which means that, one corner is perfectly thinned to the thickness you want, but the other corner is too thin, or even gone. So the main message is that this can be really hard to do, this ion etching technique, this angle etching technique, its disadvantage is that it doesn't let you to make vertical structures. It just kind of limits the geometries that you can realize.
Yeah.
Yeah, that would be probably the main reason not to use it. And just the general message is that like the likelihood of success and in getting what you want seems to be fairly good with this technique compared to those others.
I see. Okay, cool. We have another question from Sandeep.
Yeah.
Well, regarding the NV center, so each of these disks will have one NV center. Is it something like that?
Well, it depends on the material that you start with. So if you start with the sort of budget or like what they call optical grade diamond samples, which these are in this particular case, then you have about 100 NV centers per micron cubed, roughly. Okay. If you start with a very pure sample, then you have much fewer, and you would only have a few NV centers per microdisk.
Okay, few NV centers. So the reason why I'm asking this question regarding the previous slides, you have mentioned this interesting problem is that it's very hard to get a diamond thin film on silicon or any other substrates.
Yeah.
So because like the biggest problem is growing a dislocation-free diamond on a pseudo substrate or a silicon substrate, you can say.
Yeah.
So the thing is, if the spacing between these two dislocations, which are usually there in these thin films, so what's your comment on like would the NV centers be still active or the dislocations would kill them?
Yeah, I mean that's a good question. That I'm probably not the best person to answer, but I can give you some perspective. So there are groups that, of course, for many years have been trying to grow diamond on different substrates, and like silicon carbide is one that's been used, and I think gallium nitride as well. And the silicon carbide work that I'm thinking of, this has actually resulted in some early discoveries or maybe studies of silicon vacancies, because of the way that the diamond is grown onto the silicon carbide. It resulted in the incorporation of silicon into the diamond. But I don't think so. I guess what I'm trying to say is that yes, if you were to able to grow it onto a different substrate, there would be some consequence from that in terms of the types of defects you see. I don't see there necessarily being a fundamental problem with creating NVs, though, in a material that you could grow on a different substrate if you could do that. But it is important that you have good crystal properties. I think as long as you achieve that, then you could probably get good NVs.
Okay. So
and high purity too.
Because the contaminations.
Sandeep, can I interrupt? Maybe if you have detailed questions, maybe we can take them at the end of the.
Sure. Okay.
Yeah. Please go ahead. Yeah.
Okay. So what these disks are optically are whispering gallery mode cavities where we can take light and couple them into an optical resonance where photons circulate around the outside of the disk. And they do this just through total internal reflection. And of course, these types of cavities have been studied in many different material systems and for a long time, starting even with like aerosol droplets, which are just spherical optical resonators, basically. typically we characterize how good these devices are once they're fabricated by their optical quality factors as well as their mode volumes. And after refinement in our of our processes, we've created devices with optical Qs on the order of 300,000 in our very best devices, which we measure by taking light and coupling it in through an optical fiber taper. This is an optical fiber that's been heated and stretched until its diameters are on the order of a micron, which allows us to couple light evanescently into these modes. And this quality factors are very good. These are the highest that have been measured in sort of an integrated diamond photonic device. And for the purpose of optomechanics, this is important because the optical decay rate associated with this quality factor is greater than the mechanical frequency of some of the modes supported by this device, which we're going to talk about next. So to do optomechanics, what we do is we want to look at how this light couples to the mechanical resonances of this device. And you can think of, when you look at this, probably when you think of its mechanical modes, you're going to think of the device rocking or maybe twisting just because of the nature of the pedestal. And of course, those mechanical resonances or degrees of freedom exist in the structure, but they don't actually couple to light very strongly, if at all, because if you were to take your device and just twist it, you wouldn't really be changing anything about the optical path length that these photons, the photons in this cavity experience. And so there's actually no coupling between this mechanical degree of freedom and light in the structure. On the other hand, if you take your device and you actually excite a mechanical resonance where the diameter is changing, then you're changing the energy of the photons in your cavity. You're changing the resonance frequency of your cavity. And this results in a very large optomechanical coupling. Or another way of thinking about it is that light in this cavity is creating a strong radiation pressure force just because of its gradient at the edge of the cavity, which is, pushing on the edge of the structure and coupling to this mechanical resonance, which is called the mechanical breathing mode. And because our devices are quite small, so this diameter is about 5 microns, and because diamond is a stiff material, this mechanical resonance has a very high frequency on the order of 2 gigahertz in our structure. And we measure it by looking at light that's transmitted through our fiber into the cavity mode and looking at the side bands on that transmitted light. And what you find is that you have these side bands at this mechanical frequency just due to the thermal motion of the the Brownian motion of this mechanical resonance, which basically scatters photons, up and or down in energy into like Stokes and anti-Stokes sidebands. And it would normally be very hard to measure these sidebands, but our optical cavity helps us with this. Basically, it sort of converts this motion into a change in amplitude in our transmitted light. And because our quality factors are quite high and because this coupling is actually relatively strong, we can actually see these relatively easily on an electronic spectrum analyzer looking at our photodetected signal. So this was a very nice, this is kind of like the first cavitation mechanics result in our group using diamond, and was an important step for us towards doing some of the things that I talked about in the introduction. And the rest of my talk will be focused on, how we basically can harness our ability to couple to these mechanical modes to perform, interesting applications. So to start with, we'll look at cavitation mechanics for information processing. And the idea is that we have this mechanical mode. It's coupled to an optical resonance through some coupling rate. And it's also coupled to some bath, like phonons in the structure can leak out of our device. And what we've showed is that we can use this device as a memory for light, in the sense that we can take light, couple it, convert it into a mechanical motion, and then convert it back out into an optical signal again at some later time, in a way which is limited primarily by the leakage of mechanical energy into this bath. And this idea isn't new. This has been demonstrated in a few other non-diamond devices by a number of groups. We then added to this the ability to actually manipulate that stored information, which we'll talk about in a second. This interaction, can be thought of for the atomic physicists in the audience as the implementation of like a Raman system, where basically we have a strong optical field interacts with a weak probe field that contains our optical information. these beat together at a frequency difference that is equal to the mechanical frequency of our system, which then either adds or removes phonons from our system. And yeah, as I mentioned, we then showed how we can couple this to a second optical mode, which we can use to basically re-amplify that stored information, or those phonons, as well as manipulate their dynamics. Okay, so this is our first demonstration of implementing this process. What we have is a weak signal, okay, which interacts with a strong signal that's input to the cavity. These are detuned by exactly the mechanical frequency, and this resonantly drives the mechanical motion of our device. And we leave both of these fields on for some time, and then turn them both off for some time, and then turn on our strong field again. And what you see is that during this phase here, basically what we're doing is exciting the mechanical resonant motion of our device, which we're extracting from our measurement in green here. And we turn everything off, so now our device is just vibrating, but we're not looking at that, monitoring those vibrations in any way. We then turn on our strong field, and that motion modulates that field, that strong field in the cavity, and creates a sideband which contains the same coherent information that we input at the beginning of our experiment. And what you can see is that the time scale over which we're doing this experiment is on the order of microsecond, which on optical timescales is quite long. So we're sort of making a microsecond memory for light using these mechanical devices. We then added an element to this where we, during this storage process, turn on another optical field at a very different wavelength, which re-amplifies whatever motion, mechanical motion, is present in the signal through something called optomechanical backaction. And we showed that in this way we can actually extend the storage time of our optical memory by about an order of magnitude. I should mention that this, of course, comes at the cost of that we're re-amplifying everything. So we're not only re-amplifying our signal, but we're also re-amplifying any noise that is present in our system. So this will be limited as a quantum, from a quantum perspective, but for creating a classical memory, this is quite impressive, we think, in that it allows us to store information for on the order of 10 microseconds. So a second sort of information processing experiment that we did with these devices is a version of creating a photon-phonon switch through this mechanical interaction. And basically what we're creating here is a system where we have an optical mode represented in blue in our cavity, a second optical mode represented in red, and these interact with the same mechanical resonator through just the geometry of the device. So we just have two different whispering gallery modes interacting with the same mechanical resonance. And what we show is that depending on the phase of these two signals relative to each other, we can cause them to modify the response of one. So as we change the phase of one of our optical modes, we change the response that we measure in the reflection of our cavity in the phase of the second mode due to their mutual interaction with this mechanical mirror. And so the idea here is that we have like a double lambda system shown here, where these two colors are determined entirely by like the cavity mode spectrum of our device. So we just have to choose two optical modes in our device that can be separated by, in our case, are separated by about 50 nanometers in our system. And they're each driving the mechanical resonator, and they're doing this in a coherent way, which means that if we adjust the phase of that driving by adjusting the phase of our probe fields, they will either be, like driving that mechanical resonator in phase with each other or out of phase with each other, which will then affect the dynamics of that each of these resonances sees. Okay, and so this is shown here, conceptually, basically, if there was no mutual interaction, we basically have two optical resonances. These are these broad dips here, which, because of their mechanical coupling, have these very sharp dips, which are called optomechanically induced transparency dips. And this is where, on resonance, because of the presence of our strong control field, we're coherently converting information to the mechanical energy to the mechanical motion. And that's what this dip is, or this peak, I guess, inside the dip. And we are doing this twice, one at each wavelength, if there was no interaction between them. But if they're coupled to the same mechanical resonator, then what happens is that actually, if they're coupling in phase, like, or in the same, with the same phase relative to each other, the same mechanical resonator, the depth of this dip gets larger for both of them. And this is because you can imagine, if you have like these sort of three mechanical resonators, if they're moving in phase with each other, then the center mechanical resonator will move a larger amount than if there was just one resonator moving. And conversely, if they're driving this sort of center mechanical resonator out of phase, there's actually a complete cancellation, and you can have no optomechanically induced transparency dip in your system. And this corresponds to there being no mechanical motion of your center resonator. And this is what we've seen experimentally, and we've used this to build a sort of interferometer or switch between these two colors of light, 1550, 60 nanometers and 1520 nanometers, where when we just flip the phase of one of these input fields, we get a change in the transmission of the other input field. Okay, so we're flipping the phase here at time 0 of one of our fields, and then the transmission of the other field is being modified as a result. Yeah, this would be hard to do otherwise. Like, you don't normally aren't able to, create an interferometer between two colors of light very, without playing tricks like this, basically. So for the last, yeah.
Yeah, you have around 10 minutes.
Yes. So for the last 10 minutes, I'll talk about our final experiment, our most recent work, which is where we're now. Okay, so I've tried to show that we've done a good job of understanding how we can coherently control vibrations in our structure using light, and this is all done using telecom wavelengths. Now we want to see whether we can use these vibrations to modify the spins of NV centers in our diamond. And the idea is that these vibrations will couple to our spins in our system through like deformations of the diamond crystal lattice. All right. And this would allow us to implement this picture that I showed in the first slide, where we can convert a telecom photon to a phonon, and then through this stress, like this microscopic stress field, which is concentrated in the center of our device. So the edge of our device is moving, but the stress is maximum in the middle, and that will then control a spin qubit. And the motivation for this is that would let us couple telecom photons to these spin qubits, which is otherwise not possible. So the microscopic picture here is that if we have an NV center and we deform the crystal lattice in either sort of the parallel or perpendicular direction relative to the NV orientation, we can drive, well, this parallel orientation, shifts the energy levels up and down. And so we have we have a spin 0 ground state, and then we have a plus or minus 1 ground state in our system. They're split nominally by about 2.8 gigahertz intrinsically. And when we apply parallel stress, that shifts up the plus and minus 1 states relative to the 0 state. If we apply a perpendicular stress, it actually mixes the plus and minus 1 states directly. So this is what we'll be focused on in this talk. And what we want to do is see if we can create a stress field that is equal to the splitting between these plus or minus 1 states, which we can control and tune using a magnetic field. Okay, so this idea, and this is a simplified version of that picture over here, where basically we have a ground spin state, 0 spin state, and then a plus or minus 1 ground state spins. And we want to use a stress field to couple these plus or minus 1 states. And this idea is well, it was new kind of when I started in Calgary, but I wasn't the only one thinking about this. And a couple of groups, 4 groups really, actually did a lot of work just pushing their ability to use mechanics to control these spins. One of the first papers was from the Fuchs group at Cornell, where he basically shows that using like a macroscopic diamond resonator, he can modify the spin populations of these 0 and plus or minus 1 states. But none of these previous works involved optomechanics or any optical fields to control the mechanics. So this is what my group has been working on for the past few years. This is a picture of the device that we use to do this, where basically we have here, this is an optical image of an array of these microdisks. And it's placed next to them is a microwave antenna that we need to use for initializing and helping with the readout of our NV centers. And that zoomed in optical image created with the confocal microscope of one of these devices is shown here. This is the device. Next to it is the optical fiber taper that I showed earlier. And just to give you an idea of scale, this is our microwave circuit here. And the idea is that we want to basically, control spins in this device here using our mechanics. And then we use some optics just for reading them out. So to do this, we perform similar experiments to what I described with optomechanical memory, actually quite a bit simpler in some ways, where we just optomechanically heat our device. So basically, we're going to excite motion of our device so that it enters a regime of mechanical self-oscillation. And we do this by turning on our laser at telecom wavelengths input to our cavity in a way that's just Bluetooth tuned by the mechanical frequency relative to our optical cavity. And this, in a manner very analogous to laser cooling, excites the device into sort of self-oscillations, whereas as we turn up the power in our drive laser, our mechanical motion goes from being very small to several orders of magnitude larger in a way that's analogous to sort of phonon lasing. And this creates a stress in our system, which is on the order of 20 megapascal. So you can basically imagine a 20 megapascal stress oscillating at about 2 gigahertz in this device. And we can actually control the frequency of these oscillations by injecting a tone that we can tune, which is just a little bit detuned from this drive laser, and that gives us kind of like a fine tuning of the exact frequency at which these mechanically oscillate. And this creates stress in our device, which, as I mentioned earlier, is concentrated in the middle. And our goal is basically to look at how that stress modifies the spin states of the NVs at that point. So first, before we can do this, we have to use a magnetic field to tune our NVs so they have spin states that are separated by exactly our mechanical frequency. So this just shows that we've done that. These 3 dips correspond to actually different nuclear spins associated with a given electronic spin state. But the 0 nuclear spins in this example are separated by exactly our mechanical, or very close to our mechanical frequency. We characterize the NV spins. I won't go through this except to say that they have coherence times that are on the order of microseconds and T1 times that are on the order of milliseconds. And we also characterize our ability to control our mechanical vibration frequency using our injection locking technique. And we show that we have pretty large tuning range on the order of 5 megahertz, but that, as we tune our mechanical self-oscillation frequency, its amplitude will go down. So this makes things a bit more complicated for us. So that, but over some sort of 400 kilohertz bandwidth, we can adjust our mechanical vibration frequency. And so what we then measured is the spin population in +1 or -1 as a function of the mechanical oscillation frequency. And what you see is that when our mechanical oscillation frequency comes onto resonance with +1, if we initialize our NV into +1, then our mechanical motion will transfer population back down to -1 and create a dip in our measurement. And similarly for -1, if we start in +1, we will see population transferred into -1, resulting in a peak. And this was a really exciting measurement for us to show that, indeed we've optomechanically excited these vibrations and caused them, use them to then modify our spin populations in these devices. The data on the left shows that if our system isn't on resonance, then nothing really happens. Okay, so this corresponds to a scenario where our stress field is not resonant with our transition. And so this is the first demonstration of sort of optomechanically modified spin populations in these diamond devices. So everything that I've described so far is still pretty far from being a really quantum interface. Okay, so if you look at this system, we have basically a lot of photons creating a lot of phonons, and then those are coupling to a quantum spin. Okay, in our case, it's coupling to an ensemble of about 10 spins probably, but that isn't really very important. It doesn't, the fact that there's more than one doesn't help us really. But certainly we can't say that we've built a fully quantum interface. And we can characterize this by something called the cooperativity, where basically our spin mechanical cooperativity is about 10 to the -9. Our optomechanical cooperativity is good. It's on the order of 1. That's necessary in order to have this coherent operation. But what we really want to do to build something useful for quantum networking is get this spin mechanics cooperativity to go way up. And to do that, we probably need to replace our NV center with a different spin qubit, or use the excited state manifold over NV. And we can get into the details of this if people are interested. But the main message is that one of the reasons the NV center works at room temperature, at least in the ground state, in the sense that it has good coherence, is that it doesn't couple very strongly to phonons. But this, of course, means that its stress coupling isn't very big. So to build a quantum version of this, we will need to either go to low temperature, or we will need to go to low temperature, and we probably want to look at a different diamond spin qubit. But so that's the bad news. The good news is that if we do this, then it's totally within reach to get spin cooperativity, mechanics cooperativity equal to 1 or even greater than 1 if we change our device geometry into a optomechanical crystal, which our group is creating, as well as has been demonstrated by other groups in the world already. And so this sort of lays out our path for the next few years to advance this work. And I just want to finish now by acknowledging, all of our group members, but particularly, so Matthew Mitchell joined my group when I founded it actually many years ago as an undergrad. He's now a postdoc at UBC working on silicon photonics. David Lake is now a postdoc at Caltech. These two guys really perfected our optomechanical diamond devices and then conceived of all of the memory experiments. And David Lake and Pursoon really worked super hard to make the NV spin stress coupling experiment happen. And they were assisted by Denis Sukachev, who also, without him, that experiment wouldn't have worked. And then, of course, other group members have contributed to some other experiments that I didn't have time to talk about today, but these, I just wanted to highlight the major contributions from these guys. Okay, so I'll stop here and welcome any questions that you might have.
Thanks, Paul, for the wonderful talk. The floor is open for questions. Akshay, please go ahead.
Thanks, Paul, for the talk. Can you hear me?
Yes.
So is there a specific reason you picked the Whispering Alley mode kind of thing as opposed to the one you talked about in the last slide, the optomechanical crystals? Is there a specific advantage other than the large cooperativity that you're talking about?
No, I mean, probably like from a pure performance point of view, at least theoretically, the optomechanical crystal will be better. Like you'll get larger per phonon coupling, you get larger per photon, like larger spin photon coupling, you get larger photon coupling. And you can, in theory, have higher mechanical dissipation. The reason we use microdisk is that, we're sort of en route to making these optomechanical crystals.
I see.
And said, well, let's try to make some microdisks first just to see what the limits of your fabrication are. Like microdisks are very good for allowing you to quickly assess how good your etching is and what the limits for creating high optical Q cavities is. And then it turned out that, you know, their mechanical properties were also much better than we expected. So the mechanical quality factor is on the order of 10,000, which is a lot better than I've been seen in previous microdisk structures. So, right. So the idea was to make these, and we are working on that. But the fact that these microdisks support lots of optical modes, so they have an optical mode spaced every a high Q mode every 20 nanometers or so. It depends on your diameter, but this was important for letting us do all of the multi-mode stuff that I talked about. It would be hard to do that in the photonic crystals.
Sure. Okay.
And then another actual kind of advantage, which is very not obvious, is that the fact that our optical field doesn't overlap with the point of high stress in these devices was important for the experiment that we did, actually. Because the really strong IR field, which is driving this mechanical motion, would actually have some effect on the charge state of these NVs, which might be a problem in these optomechanical crystal cavities. But you know, there might be a way to work around that. But yeah, it did end up being sort of lucky that we were working with these devices for these experiments.
Okay, yeah. Cool. Thanks.
Yeah, Shankar, please go ahead with your question.
Yeah, I have similar line of question. Like actually, I think Paul answered partially. So the 1D crystal beam structure that you say that would be better because of the overlap, but you also have intrinsic stress. Is there an intrinsic stress in these structures that you have to negotiate? Like you mentioned, the disk, you know, you're not actually overlapping your field with the high stress region. So is that an advantage, or you have to do some negotiation to take care of the intrinsic stress?
I mean, for this specific experiment, the intrinsic stress didn't have a big effect. Like the static stress doesn't really affect your ground. It does affect your ground states, but not a huge amount. When you talk about optical excited states, intrinsic stress becomes very important. And if you go to silicon vacancies, it will also be important, where there's larger per phonon coupling. So in the short term, it hasn't been a problem. In the long term, it probably will be important. I can't say necessarily whether our system is better or worse than that, but in a sort of related, you know, aspect, if you look at optical transitions of spins in these photonic crystal structures, it is hard to get really sharp optical transitions because of the prevalence of lots of surfaces and as well as stress that will always be nearby your spins. Okay. This has actually prevented anybody from doing really nice NV center quantum optics experiments in these cavities. Yeah. Whereas the microdisc would be probably a little bit easier to manage that. Yeah.
Right. In microdisc, I think it's little forgiving when it comes to these things, but this is about coupling to a particular optical mode. So since you are using disk, not a wire, you do have azimuthal modes there, right?
Yeah.
So how do you control? What is the thickness, by the way? I missed that somewhere. Like I couldn't catch it.
It's about 400 nanometers.
So 400 nanometers. So you will have multiple modes there. So both TE, TM, and then you will have higher order modes and azimuthal modes inside. How do you control that? It's you have to spend enough time to really catch the right coupling position to identify, or rather excite the right mode here, optical mode.
Yeah, I mean so you're right. There's a wide spectrum of modes. Because these are quite small, the spectrum isn't as dense as you would see. Like if you look at a really big microdisc, 100 micron microdisc, then you see modes, every space by, less than a nanometer, right? So you would have, but here our spectrums are actually quite simple. I can try to get up a plot at some point, but actually, yeah, why don't I?
Right, I couldn't.
But my point is that they're spaced by like nanometers, if not many nanometers. And so you do have to know what you're doing in order to know which modes are which, if that's important to you. Typically, we just end up setting the highest Q mode, which is usually the fundamental TE mode. And it's just a question of adjusting the wavelength,
Yes, I get that.
Yeah.
So you mentioned that the highest Q you are getting for a TE mode, but I would expect the highest Q for a TM mode, isn't it, for a disk, because you do have surface roughness that is contributing to TE edges, but TM mode will not suffer because the top layer and the bottom layer, they don't see the hard isotropic edge, right? Or anisotropic.
Yeah, I mean, it's so that's a good point, and I guess I shouldn't have been as confident in saying that the fundamental TE. I should have said the fundamental TE or TM mode. I wouldn't say that we have like definitively ruled out one versus the other. I mean, you are etching the bottom surface, but I'm trying to remember whether we have like convinced ourselves that it was the TE or TM. I feel like we've seen high Q modes in each, without one necessarily being, much worse or better than the other. But
I see.
Yeah, that's a good question.
But that's easy to do. You just look at the group index and you should be able to figure out which one is better. Okay, good. Thank you.
Okay, Nilesh, please go ahead with your question.
Hello, am I audible?
Yes, you're audible. Please go ahead.
Okay. Yeah. So for the optomechanical induced transparency experiment that you showed, so you depicted a 3-level system there. So does that mean you're operating in a low temperature regime? So because of which you have just 3 levels here.
No, so we definitely aren't operating in a low temperature regime. And if you look at this picture, I had it earlier. Yeah. You have this n phonons would be could be a big number. I'm not sure if that's really what you mean. I mean, you're gonna have some thermal phonons, and then on top of that, you have a large number of coherently excited phonons, and your optical field is coherently adding or subtracting phonons from your system. And in our experiment, we definitely aren't in a low temperature region. These are all at room temperature. You could go to low temperature and nothing would really change. You would just have less noise. So I haven't included noise here, but if you were to sort of determine the smallest number of phonons you could create and then reversibly read out, you would be limited in our experiment by the thermal population. And if you wanted to get the regime where you're just adding one phonon or removing one phonon and observing that and being able to measure that, you would need to be at low temperature. But for our experiments, we're driving a lot of phonons.
Okay.
Yeah.
Okay. Thank you.
Yeah. Yogendra, please go ahead with your question.
Thank you, Professor Paul, for a very interesting talk, particularly the experimental work. I'm a mechanical engineer, and I was really excited to hear that you had this quartz diamond, microdisk oscillating at 2 gigahertz with 20 megapascals. So I was just wondering, the mechanical engineer, what would be the typical fatigue like? These things may or may not be able to give you more than a couple of million cycles of life. So I was just wondering, from a mechanical engineer's viewpoint, how would you be able to ensure that these devices give a good amount of service? I hope you got my question.
Yeah. So you're asking how long do they last, basically?
Yeah, because you are checking them at 2.1 gigahertz at 20 megapascals or so. So I was worried as a mechanical engineer, how would this photomechanics approach help in terms of life of the devices that you may wish to build?
Yeah, so that's a good question. I mean, we haven't done, probably by an engineer standard, we haven't done any specific
Anyway, thanks for. I had another question. Is
sorry, I'll just mention some like. I'll just say some anecdotal things, which is that we fabricate the devices, 300 kilometers away. We bring them down to our lab, and they never break. So they're actually quite robust. And then in our spin mechanics experiment, actually all of these experiments were done with the exact same device. And it did degrade though slowly. So its mechanical quality factor started at 10,000 and ended at about 4,000. So something is happening to our device during our experiments over the course of years. We think that that's probably, it's just getting dirty, maybe from our microwave wire that's nearby. And we could take it and try cleaning it again and seeing if that improved its mechanical quality factor again. But that's the only noticeable degradation that we've observed so far.
I also wanted to ask you, what is your G rate coming out of the mechanical part of the system? I know you talked about the optical part. What was the Q factor for the mechanical part?
Yeah, this device started at 9,000, and it reduced over many years to about 4,000. We have made devices recently where our quality factor is about 40,000. That's our best that we've seen. Although we have to be very careful to make sure that we're not, amplifying that, like that we're not narrowing that artificially during our measurement. Yeah, so that 10,000 is kind of the range that we see in our devices, and this is limited by how small this pedestal is, basically. So, like, if you have a big pedestal here, then our Q will be very low. Like in this device, you would never be able to see any mechanics.
Okay. Last question is that when you were able to reconstruct the weak signal in some of those experiments, is something like holography where we actually record something and reconstruct the same thing? Is it something like that?
Yeah, in the sense that it's coherent, I guess. It's an interference process that we're relying upon to see it. So yeah, there probably are some analogies there.
Thank you, Professor Paul, for a fantastic talk.
Thank you.
Ambarish, please go ahead with your question.
Yeah, hi, nice talk, Paul. I was just wondering if there is some way, rather than the directly coupling through the stress of the vibrations, the stress-mediated coupling with NV spin.
Yeah.
Has there been any attempts to try to maybe have an intermediate magnetic coupling, through some magnetic dots or something? Is that possible?
Yes. So that's definitely a very good question. So the answer is yes. I think so Melatinsky, who I mentioned here, he was a postdoc at Harvard, and I think they did exactly that, where you had like a standard NEMS resonator and put a magnet on the end, and that tip was used to sort of do some kind of sensing of an NV through a magnetic field. And more generally, I mean, theoretically, that's probably the better approach, or at least it's a very good approach to getting a strong coupling. It might be hard to get to work at these gigahertz frequencies, but at lower frequencies it's possible. But it hasn't really been demonstrated in the sort of context of these optomechanical devices yet. But it's something that we've thought about, and it would definitely be it's worth considering. It's still hard theoretically to get a strong enough coupling. You need a very sharp magnetic tip with a strong gradient, but in principle, it's a good way to go.
Thank you.
Yeah, I guess that was the last question. Thanks again, Paul. Maybe everybody can either unmute themselves or just use the applause emoji to applaud Paul for the wonderful talk. Thanks, Paul. I think these are the maximum number of questions we have received after the talk. So hopefully that means people are very interested. Great, Paul. So if there are no further questions, then maybe we can end this session.
Okay. Well, I just want to thank you for staying up late. I know it's not the greatest time for a colloquium.
No, it's totally fine. It's like 8:20 right now, so it's not too bad. Yeah. Thanks, Paul. Take care.
Okay. Thank you for inviting me. I hope to see you in person someday.
Yes, that would be great.